Imagine scientists confirm tomorrow that a telescope has taken the deepest image of the early universe ever made. The image covers a region of sky smaller than a grain of sand held at arm's length. It contains thousands of galaxies. Some of them are so ancient their light left its source before the sun existed, before the Milky Way had taken anything close to its current shape, before most of the observable universe had formed any structure worth calling a galaxy at all. Scientists look at the image and feel something close to triumph. This is what the instrument was built to do. This is confirmation. Then they look at the numbers. The galaxies are too massive, too bright, too chemically mature, too structured. Under the standard model of cosmology, the framework built from a century of observation, tested against everything from the echo of the Big Bang to the large-scale architecture of 100 billion galaxies, objects like these should not exist at this age, not at this mass, not with this chemistry, not in these numbers. Tonight, we go through what Webb was built to see, what it found in that grain of sand patch of sky, and why the early galaxies it detected are not supposed to be there. We go through what the data says, what the scientists know, and what is being said quietly in the corridors of every major cosmology conference in the world right now. Subscribe before we continue. We begin. There is a fact about light that sounds simple until you stop and follow it all the way down. When you look at anything, a lamp across the room, a mountain 40 kilometers away, a star on a clear night, you're not seeing it as it currently is. You're seeing it as it was at the moment the light reaching your eye left its source. For nearby objects, this delay is so small it does not register. The moon is 1.3 light seconds away. The sun is 8 light minutes. The Andromeda Galaxy, the most distant object you can see with unaided eyes, is 2.5 million light years from Earth. The light arriving from Andromeda right now left that galaxy 2.5 million years ago. The hominins who were alive when that light departed did not yet have language. Every human civilization, every war, every empire, every language ever spoken, every person who ever lived, all of it occurred after that light had already been travelling for 2.5 million years. Webb does not look across space. It looks back through time. Those are not the same thing. This distinction is the foundation of everything the telescope was built to accomplish. The goal was not simply to see farther. The goal was to see earlier, to capture light from epochs so ancient that the universe's own expansion had fundamentally changed that light's character during the billions of years it travelled toward us. Here is what expansion does to light. Space is not static. It has been stretching since the Big Bang, and it stretches the light travelling through it. As a photon travels across an expanding universe, its wavelength lengthens. Light that began as visible radiation, the narrow band human eyes evolved to detect, shifts over billions of years of travel into the infrared. By the time light from the universe's first few 100 million years arrives at Earth, it occupies a part of the electromagnetic spectrum entirely invisible to the human eye and to most instruments ever built to look at the sky. Hubble was not built for this. Hubble's genius was in the visible and ultraviolet range. It could detect some near-infrared, but its sensitivity fell sharply at exactly the wavelengths where the oldest light was arriving. The galaxies that existed in the universe's first billion years, the objects that mattered most for understanding how everything began, were effectively invisible to the most celebrated telescope in human history. Webb was built to close this gap, and only this gap. Its mirror spans 6.5 meters, 2.7 times wider than Hubble's, which means roughly 6 times more light collecting area. Each of its 18 hexagonal segments is coated in gold, 48.25 grams per segment, less than a golf ball's worth across the entire surface, chosen specifically because gold reflects infrared light more efficiently than any other practical coating. The instrument runs at -233 degrees Celsius, just 40 degrees above absolute zero, at the second Lagrange point 1.5 million kilometers from Earth, behind a sun shield the size of a tennis court that permanently blocks the sun, the Earth, and the Moon from warming the detectors. At those temperatures, the telescope's own thermal emission becomes negligible. The faint infrared signal from the early universe has almost no background noise to hide within. This is not a general-purpose instrument. It is a machine built for a single measurement in a single part of the electromagnetic spectrum at a single range of cosmic distances. 30 years. $10 billion. The entire engineering effort aimed at one capability: receiving light that has been travelling since before the Milky Way formed and characterising the objects that sent it. The question was what those objects would look like. The models had a specific answer. The universe, it turned out, had a different one. Before the first data arrived, the scientific community had specific quantitative predictions about what high redshift galaxies would look like. These were not rough qualitative guesses. Simulation projects running on the most powerful computers in the world, Illustris TNG, Eagle, FLAIRS, had modelled the galaxy population at redshifts up to Z*10 and beyond using lambda CDM physics, predicting luminosity functions, mass functions, and number counts at levels of detail that could be directly compared to what Webb would find. The predictions were confident. They were built on decades of lower redshift validation. When Webb's data arrived, the predictions were tested directly and systematically for the first time. They failed in a specific, quantifiable, and consistent direction. In its first year of science operations, Webb returned data at redshifts no previous instrument had cleanly resolved. Redshift 10, Redshift 12, Redshift 16. Each number represents a further reach back into cosmic time. Redshift 10.9 corresponds to a universe 400 million years old, less than 3% of its current age. The light arriving at Webb's detectors from those distances departed before the solar system existed, before Earth existed, before the atoms comprising everything you have ever touched had assembled into their current arrangements. What the telescope found at those distances was not what the models predicted. Not because the models were carelessly made, not because the observations were poorly executed, but because the early universe, at the moment Webb was finally able to see it clearly, turned out to contain things that should not have had time to be there. Picture a patch of sky, not a wide arc, not the spread of a hand held overhead. A pinhole, a region so small that if you held a grain of sand at arm's length and tilted it to expose its narrowest edge, that edge would cover the entire area. No stars visible to the naked eye, no known galaxies in any catalogue. Nothing flagged as interesting at any wavelength by any previous survey. A grain of sand held at arm's length. That is the window through which we saw the edge of everything. The methodology of deep field imaging has a specific history that matters here. In December 1935, the Hubble Space Telescope pointed at a blank region of sky near the Big Dipper and stared for 10 consecutive days. 342 individual exposures. The accumulated light resolved into an image containing approximately 3,000 galaxies, some of them so distant their light had been travelling for over 10 billion years. The Hubble Deep Field. It permanently changed the meaning of the word empty in astronomy. There is no such thing as empty sky. Every blank patch of sky contains galaxies, billions of them, stacked at different distances, their ancient light arriving simultaneously at any detector sensitive enough to gather it. The darkness between the stars is not absence. It is light we did not have the means to collect. Hubble proved this for visible light. Webb would prove it for infrared, and at distances 10 times greater. Hubble refined this technique for decades. By 2004, the ultra-deep field had resolved approximately 10,000 galaxies in a region covering 1/10 the apparent diameter of the full moon, 11.5 days of exposure. The image became the standard reference for early universe research, a core sample drilled through the visible cosmos. But Hubble had a ceiling. The most ancient galaxies, objects at redshifts above 10 or 11, were either invisible entirely or appeared as marginal signals whose properties could not be reliably characterized. The infrared gap swallowed them. The most important period for understanding how the first structures formed was also the period least accessible to the instruments available. Astronomers knew what they could not see. They just could not see it. When Webb's first deep field image was released in July 2022, it covered a region centered on the galaxy cluster SMACS J723. The image extended to redshifts Hubble could not cleanly resolve. Thousands of galaxies appeared in a region smaller than Hubble's ultra-deep field. It was produced from 12.5 hours of total exposure. Hubble needed 11.3 days to achieve its deepest comparable result. Webb was not an incremental improvement. It was a different category of instrument. Within weeks, research groups around the world were independently analysing the data, identifying high redshift candidates through photometric redshift estimation, comparing each galaxy's brightness across multiple wavelength bands to find the characteristic break in the spectrum caused by neutral hydrogen-absorbing high-energy photons. This Lyman break shifts to longer wavelengths as redshift increases. At redshift 10, it falls in the infrared bands Webb was specifically designed to detect. The photometric redshift catalogues from Webb's early programs began returning candidates at redshifts no previous instrument had clearly detected. Objects tentatively identified at redshift 16, representing light that would have left its source just 250 million years after the Big Bang, in a universe not yet 1/50th of its current age. Among the objects resolved in Webb's early programs was a galaxy Hubble had previously detected only at the absolute edge of its capability, a marginal signal whose distance could be estimated but whose properties could not be characterized. Its catalogue designation is GNZ11. The Z11 notation indicates its redshift, approximately 10.9. That corresponds to a look-back time of 13.4 billion years. We observed GNZ11 as it appeared when the universe was 400 million years old. The light currently arriving at Webb's detectors from GNZ11 left that galaxy 13.4 billion years ago. In the time since that light departed, the entire history of the solar system has unfolded. The sun formed, Earth coalesced, life appeared, photosynthesis transformed the atmosphere, multicellular life evolved, vertebrates came ashore, dinosaurs rose and were extinguished, mammals diversified, primates evolved, hominins appeared, every human civilization, every city ever built, every war ever fought, every language ever spoken, every work of art ever made, all of it occurred after that light had already been travelling for 8.8 billion years. The atoms that now constitute everything you are were distributed through a universe that did not yet contain a solar system. Sit with that. Not as a poetic abstraction, as a physical fact about the object Webb detected and measured. What Hubble had seen as a smudge, Webb resolved as a galaxy with measurable stellar mass, a galaxy with measurable luminosity, a galaxy with a measurable chemical composition. And when those measurements were compared against what the dominant theoretical model predicted should be physically possible at that age, the comparison produced a discrepancy that no combination of measurement uncertainty could account for. GNZ11 was not alone. Across multiple independent deep field programs conducted in Webb's first year of operations, a consistent pattern emerged. Galaxy after galaxy at high redshift was coming in brighter, more massive, and more chemically mature than the models allowed. Not at the edge of the model's allowed range, 3 to 5 times above the model's predicted maximum. The confirmation process for each candidate, photometric identification, then spectroscopic follow-up, then independent reanalysis, filters out noise. What remains is signal. And the signal was pointing somewhere the models had not anticipated. The framework is called lambda CDM. Lambda is the cosmological constant, the term representing dark energy, the component of the universe responsible for its accelerating expansion, confirmed in 1998 when 2 independent supernova survey teams discovered the universe's expansion was speeding up rather than slowing down. CDM is cold dark matter, invisible, interacts only gravitationally, required by the evidence but never directly detected. Lambda CDM describes a universe of 5% ordinary matter, 27% dark matter, 68% dark energy, with structure forming through a specific process called hierarchical assembly. GNZ11 is not supposed to exist. The model says so. The model is wrong. Hierarchical assembly works like this. The Big Bang was nearly uniform. Nearly, but not quite. Quantum fluctuations left the primordial distribution of matter with tiny variations in density. Regions fractionally more concentrated than average. Over hundreds of millions of years, gravity amplified these variations. Denser regions pulled in surrounding matter. The first structures to form were dark matter halos, gravitational scaffolding on which ordinary gas collapsed, cooled, and eventually ignited into the first stars. Those first stars, or a hypothetical population called Population 3, never directly observed, formed from pure primordial hydrogen and helium, with no heavier elements. They burned fast, died in supernovae, seeded the surrounding gas with the first carbon, oxygen, nitrogen, iron. Second-generation stars had richer chemistry. Collections of stars in dark matter halos accumulated into the first recognizable galaxies. Smaller galaxies merged into larger ones. Structure grew through accumulation, small to large, over time. This is not an assumption. It is the mathematical consequence of gravity acting on small initial fluctuations over cosmological timescales. This process has a rate. Dark matter halos can only grow as fast as gravity acting on the density fluctuation spectrum allows. The model predicts, with mathematical precision, the maximum stellar mass a galaxy can contain at any given cosmic epoch. At redshift 10, a universe 480 million years old, the model's upper bound is a few 100 million solar masses, the absolute ceiling, the most extreme outlier the physics allows. GNZ11 contains approximately 1 billion solar masses of stars at redshift 10.9, in a universe 400 million years old. That is 3 to 5 times above the predicted maximum, not for a typical galaxy, but for the most extreme object the model considers possible. It is the equivalent of conducting a geological survey and finding, in a sediment layer dated to 10,000 years ago, a fully assembled internal combustion engine in working condition. The object is not supposed to exist at that depth. It is too complex, too processed, too finished for the age of the layer in which it appears. To make the scale of the discrepancy concrete, Lambda CDM predicts that at redshift 7 to 8, galaxies with stellar masses above 10 billion solar masses should be extraordinarily rare, on the order of 1 per cubic gigaparsec, where a gigaparsec is approximately 3.26 billion light-years. The observed number density in Webb's early deep field data was higher than this prediction by roughly a factor of 10 to 100, depending on how the sample is defined. Now, here is where the false hope ladder begins. Because science does not accept anomalies passively, It generates explanations, and every explanation for GNZ11 has been tried. The first rescue, photometric mass estimates, are unreliable. The initial stellar mass measurements used photometry, inferring mass from brightness across multiple wavelength bands. Photometric estimates carry systematic uncertainties. If the true mass were lower than estimated, the problem might shrink to a manageable size. That rescue failed. GNZ11 received detailed spectroscopic analysis from Webb's near-infrared spectrograph, which splits a galaxy's light into its component wavelengths and identifies specific spectral lines produced by different elements at different temperatures. The spectroscopy confirmed the redshift. It confirmed the luminosity. And it found something that was not expected at all: a nitrogen to oxygen ratio approximately 3.4 times the solar value. Nitrogen at that level requires multiple generations of stellar cycling, stars forming, burning, dying, enriching the gas, next generation forming from enriched gas, repeating. Multiple complete cycles of stellar evolution in 400 million years. The spectral fingerprint of GNZ11 describes a galaxy that has already been doing serious chemical work for a long time, in a universe that has barely started. The rescue did not rescue. It deepened the problem. The second rescue: active galactic nuclei. Supermassive black holes accreting matter at a galaxy's center produce enormous luminosity. If GNZ11 hosts an active galactic nucleus, its apparent brightness might be inflated, causing stellar mass estimates to be systematically too high. That rescue was examined. The spectral analysis found no clean AGN signature sufficient to account for the discrepancy. And GNZ11 is not the problem in isolation. GNZ11 is the best characterized example of a systematic pattern. In February 2023, a paper by Lab and colleagues published in Nature presented 6 high redshift galaxy candidates, all at redshifts between 7.4 and 9.1, all with estimated stellar masses exceeding 10 billion solar masses. The most extreme appeared to contain approximately 100 billion solar masses, twice the Milky Way's entire accumulated stellar inventory, assembled in less than 700 million years. AGN contamination and measurement uncertainty cannot explain a systematic pattern of this magnitude across independent programs using independent analysis methods. The third rescue: Population 3 stars. If early galaxies were dominated by first-generation massive stars, their light-to-mass ratio would be far higher than models calibrated on nearby galaxies assume. Apparent masses would be overestimated. The excess might not be real mass. It might be an artifact of applying the wrong stellar population template. This rescue directly conflicts with GNZ11's spectrum. A galaxy dominated by chemically pristine first-generation stars should not show nitrogen enrichment at 3.4 times the solar value. Nitrogen at that level requires exactly what population 3 dominance precludes: multiple generations of nuclear processing. The chemistry argues against the rescue designed to explain it. The fourth rescue: direct collapse black holes. In specific early universe conditions, entire gas clouds could collapse directly into massive black holes, bypassing the stellar phase entirely, producing seeds massive enough to grow rapidly and contribute luminosity mimicking stellar mass. This rescue is legitimate. It is also unconfirmed. No direct collapse black hole has been observed. The specific observational signatures have not been identified in the GNZ11 system at the levels required for direct collapse to explain the full mass discrepancy. A 2023 analysis by Boyle and Colchin examined the statistical significance of the Laber et al.'s candidates within the Lambda CDM framework. The conclusion: if even one of the most massive candidates is confirmed at its estimated stellar mass, the tension with the model exceeds 5 sigma. 5 sigma. The probability of the gap arising from random measurement scatter is less than 1 in 3.5 million. In particle physics, 5 sigma is the threshold for claiming a discovery. In cosmology, 5 sigma against a model means the model and the data are in serious, robust structural disagreement. Several candidates have since received spectroscopic confirmation. Masses have come in somewhat lower than photometric estimates in some cases. Lower confirmed masses help. The pattern does not disappear. The systematic excess of bright, massive early galaxies over lambda CDM predictions persists across multiple independent datasets, analysed by multiple independent teams, confirmed spectroscopically in multiple individual cases. Not one anomalous object. A pattern, not a measurement error. A confirmed systematic excess. Not on the edge of the model's allowed range. 3 to 5 times above the maximum. If you are listening in the dark, let this rest with you for a moment. 6 candidate galaxies, all of them exceeding the mass the standard model says the entire early universe was capable of producing in its most extreme objects, not by a small margin, by amounts that, if real, require something the model does not currently contain. If this channel is where you come to sit with the actual shape of the universe, a subscribe helps us continue making this kind of work. Scientific models fail in a specific sequence. First, the measurement is questioned. Instruments miscalibrate. Analysis pipelines have bugs. Systematic effects propagate unexpectedly. Questioning new results is not denial. It is methodologically correct, and it is the first thing that should happen. If the measurement survives scrutiny, the model is modified at the margins, a parameter adjusted, an additional process included, an assumption relaxed. If anomalies accumulate past the point where marginal adjustment is sufficient, the model faces genuine revision. Full paradigm replacement is rare and slow. The Hubble tension existed before Webb. Webb made it impossible to ignore. The Hubble constant is the number describing how fast the universe is currently expanding. Every independent measurement method should produce the same value if the standard model is correct. 2 independent chains of measurement do not agree, and have not agreed for years. The first chain uses the cosmic microwave background, the thermal radiation left over from 380,000 years after the Big Bang, when matter and radiation first decoupled. The Planck satellite's precision measurements yield a Hubble constant of approximately 67.4 km per second per megaparsec. The second chain uses Cepheid variable stars and Typea supernovae, a distance ladder built from nearby calibrators extended to distant galaxies. This collaboration consistently measures values around 73 km per second per megaparsec. The difference between 67.4 and 73 is approximately 8%. In precision cosmology, 8% is a 5 sigma discrepancy. The probability of the gap arising from random measurement error is less than 1 in 3 million. Both chains have been checked, rechecked, and extended with independent calibrators. The tension has not narrowed as measurements improved, it has sharpened. This is the behavior of a real physical discrepancy, not a measurement artifact. Take a breath here. 2 different methods of measuring the same fundamental constant. One anchored to the physics of the very early universe, one anchored to the local universe we can directly observe, produce answers that disagree at a level that cannot be attributed to chance. Lambda CDM, in its standard form, has no mechanism to produce this disagreement. The model predicts one value. The universe appears to have 2. Now the cascading failure begins, because the early galaxy problem and the Hubble tension are not obviously caused by the same missing ingredient. They might be independent failures in different sectors of the model's architecture. They might share a root. What matters is what happens when you try to fix one without breaking the other. Early dark energy models propose the universe underwent a brief phase of additional accelerated expansion in its first 100,000 years before the CMB was produced. This would shift the CMB-derived Hubble constant upward, partially resolving the Hubble tension. It could also alter the growth rate of early structure, potentially allowing more mass to accumulate faster. Whether the same modification resolves both tensions simultaneously at the required quantitative level without violating the CMB power spectrum at small angular scales remains an open and unresolved question. No proposed version of early dark energy has simultaneously resolved both tensions to the satisfaction of the observational community. Each attempt has resolved one thing and damaged something else. The fundamental difficulty with the early galaxy problem specifically is the nature of the prediction it violates. The model does not merely assert that early galaxies should be less massive than what Webb found. It predicts a specific quantitative upper bound on mass at each cosmic epoch, derived from first principles of gravitational dynamics operating on the density fluctuation spectrum the CMB tightly constrains. This is not an adjustable parameter. Changing the upper bound requires either more time for structure to grow than the Big Bang chronology provides, a mechanism for gas to convert into stars dramatically faster than observed anywhere, additional matter not in the standard inventory, or an initial power spectrum significantly different from what the CMB measurements constrain. None of these are minor adjustments. Each is a revision of something the model treats as a measured input. Star formation efficiency arguments fail the same test. If early galaxies converted gas to stars at dramatically higher efficiency than anything observed in the nearby universe, approaching 100% of available gas, the mass budget could be partly reconciled. But GNZ11's chemical enrichment suggests normal or near normal stellar processing, and efficiency arguments require explaining why the feedback processes that reliably suppress star formation everywhere they can be studied, radiation from massive stars, supernova explosions, AGN jets, were absent or ineffective in conditions that are now observationally confirmed to have produced chemically processed galaxies at 400 million years after the Big Bang. Dark matter alternatives offer no relief. Warm dark matter models predict fewer massive early structures, not more. Fuzzy dark matter and self-interacting dark matter likewise suppress small-scale structure. Every alternative dark matter physics proposed for independent reasons makes the early galaxy problem worse rather than better. If the early galaxy excess requires new physics, it is probably not in the dark matter sector. Lambda CDM gets a great deal right. The CMB power spectrum, Big Bang nucleosynthesis, large-scale structure, acoustic oscillations imprinted in the distribution of galaxies. These are not marginal agreements. They are precise structural matches between theory and observation across decades of data. Any modification must preserve all of them while accommodating the excess. The solution space is genuinely narrow. Narrow is not empty. But narrow means that finding a path through it requires either theoretical insight or a long process of systematic model building and elimination. What Webb has done is move the early galaxy problem from possible anomaly to confirmed pattern requiring theoretical explanation. That transition changes the scientific obligation. The question is no longer whether to take the data seriously. The question is what the data requires. The telescope was advocated for across 3 decades with a consistent message. Webb would see the first galaxies and test the standard models, predictions for early structure formation. Every agency review, every congressional testimony, every press event made this case. No presentation suggested the possibility that what Webb found might not fit the model used to justify Webb's existence. That is not dishonesty. Science cannot know in advance what a new instrument will find. But it creates an unusual situation when the instrument works perfectly and returns data that strains the theory that justified its construction. No press release calls it a crisis. Every private conversation does. The vocabulary of public scientific communication follows a precise hierarchy. Results that confirm model predictions, consistent with theoretical expectations. Results at 2 sigma tension, interesting. 3 to 4 sigma, unexpected or puzzling. 5 sigma or above, challenging our understanding or surprising. Each step is a significant escalation in actual scientific severity. The Webb early galaxy results are being described as challenging our understanding. That is the highest alarm level in the public vocabulary. It means the discrepancy is real, statistically robust, and currently without a theoretical explanation that satisfies the data. The vocabulary is accurate. It is also, for non-specialists, considerably quieter than the numbers warrant. The communication gap between what the early galaxy data shows and what appears in public-facing communications reflects a genuine difficulty in science communication rather than any intent to mislead. Scientists who spend careers developing a theoretical framework do not comfortably describe that framework as failing. The appropriate scientific response to anomalous data is skepticism, scrutiny, and a search for explanations within the existing framework before concluding that the framework requires revision. This is methodologically correct. It is also producing a public presentation of the situation that understates its severity. When press releases describe Webb's findings as surprising, they're accurately describing results that are statistically robust and currently without theoretical explanation. But surprising sounds like something that will be cleared up with a bit more thought. It does not convey that the surprise is 5 sigma in magnitude, persistent across multiple independent datasets, and currently without a satisfying theoretical mechanism. The candidate rescues are being pursued genuinely. Population 3 stars are actively modelled. Their existence is required by nucleosynthesis logic. The heavy elements in today's universe had to be manufactured somewhere, but their spectral signatures have not been confirmed at the levels required to explain the mass excess, and GNZ11's nitrogen enrichment argues against population 3 dominance for at least this specific object. You do not need to hold all of this simultaneously. The key point is that each proposed rescue carries specific observational predictions, and those predictions can be tested with future observations. Direct collapse black holes are being searched for with Chandra X-ray observations and ALMA millimeter wave data. The signatures exist in theory. They have not been found at the required level. The extremely large telescope, currently under construction in Chile with a 39-meter primary mirror, will take spectra of high redshift galaxies that Webb cannot yet characterize at sufficient resolution. The Roman Space Telescope will survey vastly larger areas than Webb's deep fields, providing the statistical sample sizes needed to test cosmological model predictions at the population level rather than object by object. These are not vague future hopes. They are specific instruments with specific observational programs targeting specific predictions. The timeline is years to a decade. The broader context of cosmological anomalies extends beyond the 2 most prominent. Attention in the matter, power spectrum normalization, the sigma 8 parameter, between CMB values and weak gravitational lensing surveys. Anomalies in the large-scale CMB itself, a persistent discrepancy between the number of satellite galaxies around the Milky Way and the number dark matter simulations predict. Each is individually explicable by systematic effects or statistical fluctuations. Collectively, they form a pattern of a theoretical framework operating at the boundary of its domain, producing predictions that persistently disagree with increasingly precise observations in ways that no single systematic effect has been identified to explain. The compounding barrier stack here is precise. The early galaxy excess exists. Population 3 cannot explain it for the objects with confirmed spectroscopy. AGN contamination cannot explain the magnitude or the population level pattern. Star formation efficiency arguments require new physics to justify and conflict with the chemical evidence. Direct collapse black holes are unconfirmed. Modified initial conditions face CMB constraints. Modified dark matter makes the problem worse, and every proposed unified solution to the Hubble tension and the early galaxy excess has resolved one and damaged the other. There is a third possibility that receives less public discussion, not because it is scientifically disreputable, but because it is the most structurally consequential. Lambda CDM might need replacement in the domain of early structure formation rather than repair. Not across all of its predictions. The model accounts for a wide range of observations successfully. Any replacement framework would need to reproduce all of those successes, while also generating a mechanism by which the early universe builds structure faster than Lambda CDM allows. That is an extremely narrow target. Building such a framework is the work of years or decades. When cosmologists use the phrase new physics in this context, they mean exactly that. Not a new instrument or a new pipeline, but new fundamental understanding of how the universe builds structure from the laws it operates under. Lambda CDM was itself born from an anomaly. Before 1998, most cosmologists assumed the cosmological constant was zero, that dark energy did not exist. The supernova evidence forced a revision of the universe's energy budget from roughly 70% matter to 68% dark energy. That revision was not marginal. It was a fundamental change to the composition of the universe, as described by the model. The framework that resulted from that revision is now the one showing strain. The process is the same. The timeline is different. The resolution is not yet visible. What Webb has provided is the sharpest possible statement of the problem. The early universe contains more structure, assembled more quickly than the dominant model predicted. That statement is supported by multiple independent data sets, confirmed spectroscopically in key cases, and has become better defined, not more ambiguous, as data quality has improved. The behaviour of a real signal, not a systematic artifact. The telescope is still running. The alignment of Webb's 18 mirror segments required solving an engineering problem that has no parallel in the history of ground-based astronomy. Each segment is made of beryllium, chosen because it maintains its shape predictably across the temperature range from launch to the minus 233 degrees Celsius operating temperature at L2. The segments were machined to curvatures specified in nanometers and coated in gold. After the mirror deployed in space from its folded configuration, fine alignment began using a process called wavefront sensing and control. Engineers analyzed the interference patterns produced by this slightly misaligned segments, calculated the required adjustments, and moved actuators behind each segment to sub-nanometer precision. The alignment took months. A single segment out of position by more than a wavelength of infrared light would have degraded the telescope's performance at exactly the wavelengths it was built to detect. The alignment succeeded. Webb's optical performance exceeded specification. The point spread function, the pattern a point source produces on the detector, was sharper than required. The machine works better than promised. The sunshield presents a different kind of engineering problem, thermal management at extreme scale. A structure nearly the size of a tennis court, approximately 21 meters by 14 meters, had to be folded tightly enough to fit inside a rocket fairing roughly 5 meters in diameter, then reliably deploy itself in the vacuum of space, 1.5 million kilometers from Earth, with no possibility of human assistance. The 5 layers of Kapton film are separated by gaps that allow heat to radiate away from the shield's interior, rather than accumulating between layers. The outermost layer, facing the Sun, reaches roughly 85 degrees Celsius. The innermost layer, adjacent to the mirror, sits at -233. That temperature gradient across 5 thin films, maintained indefinitely in space, required engineering tolerances that had never been achieved at that scale. When the sunshield deployed successfully in early January 2022, roughly a week after launch, it represented one of the most consequential single events in the history of space astronomy. Everything the telescope would eventually find depended on that deployment. The practical concept of infrared astronomy requires understanding why heat is the enemy. Infrared radiation is heat radiation. Every warm object emits it. Room temperature objects, walls, instrument housings, telescope structures, emit most of their thermal radiation in the mid-infrared, between roughly 10 and 15 microns. Webb's instruments cover wavelengths from 0.6 to 28 microns. If the telescope itself were warm, its own thermal glow would completely overwhelm the faint signals arriving from 13 billion light-years away. Cooling the telescope to -233 degrees, Celsius shifts its own thermal emission to wavelengths far longer than 28 microns, entirely outside the range of the instruments. The telescope becomes, for practical purposes, thermally invisible to itself. Only then can the detectors register the infrared signals from the ancient universe that are the reason the telescope was built. The entire thermal engineering challenge, the sunshield, the L2 orbit, the gold coating, the cryogenic instruments, exist to achieve this single condition. Webb's 4 primary scientific instruments each address a different part of the measurement task. The near-infrared camera, NIRCam, is the primary imaging instrument, covering wavelengths from 0.6 to 5 microns. It produced the deep field images from which the initial high redshift galaxy candidates were identified. The near-infrared spectrograph, NIR-SPEC, provides spectroscopic data across similar wavelengths. It confirmed GNZ11's redshift and measured the chemical composition of its spectrum. The mid-infrared instrument MIRI extends coverage to 28 microns, the range where the most distant and coldest objects in the universe emit most of their light. Together, these instruments allow Webb to characterize objects across a wavelength range that no previous space telescope could access comprehensively. When the first science data arrived from L2, scientists found that the telescope's optical performance was better than the specifications required. The instrument that cost $10 billion and 30 years to build worked, and what it found was not what the model said it would find. The concept of look-back time deserves careful attention, because it governs everything Webb was built to do. Redshift is a measure of how much the universe has expanded since the observed light was emitted. A redshift of ZR 10.9 means the universe has expanded by a factor of nearly 12 since that light departed its source. Under lambda CDM, this expansion history corresponds to a universe age of approximately 400 million years when GNZ11's light was emitted. The galaxy we observe as GNZ11 is not where it appears to be. It has been moving for 13.4 billion years since that light left. The version of GNZ11 that exists today, wherever it is, whatever it has become after 13.4 billion years of evolution, mergers, and star formation, has not yet sent us its current face. The light from today's GNZ11 will arrive at Earth approximately 13.4 billion years from now, assuming Earth still exists and there is something here to receive it. What Webb sees is a photograph taken in conditions that no longer exist, showing an object that has long since ceased to exist in that form. That photograph contains information that disagrees with the standard model's predictions for what was physically possible when it was taken. The practical implications of the redshift to age conversion are worth dwelling on, because they change the way distance works in astronomy compared to everyday experience. When you look at a nearby mountain, you see it at almost the present moment. When Webb looks at GNZ11 at Zetsus 10.9, the redshift tells you that the universe was approximately 1/11th of its current size when the light was emitted. The look-back time is 13.4 billion years, 97% of the universe's entire history. The galaxy we are seeing is not just far away, it is from a universe so different from today's that the Milky Way did not exist yet. The local group of galaxies had not assembled. The structures that would eventually produce our solar system, our planet, and the biology that makes observation possible were still distributed as diffuse gas clouds in the dark. Every photon hitting Webb's mirror from GNZ11 is a message from a universe that no longer exists in that form. Understanding what the message says is the work that is currently underway and currently incomplete. SMACS 0723, the galaxy cluster targeted in Webb's first released deep field, was chosen partly for its suitability as a gravitational lens. Massive clusters of galaxies bend the light from background objects, creating an effect called gravitational lensing that can magnify the apparent brightness of very distant background galaxies by factors of 2 to 10 or more. This magnification allows Webb to detect objects that would otherwise be too faint for even its extraordinary sensitivity. The price is distortion. Background galaxies appear stretched and curved into arcs, and the complication that the gravitational lens model must be well characterized to calculate the intrinsic properties of magnified objects from their lensed appearances. Webb's programs use both lensed and unlensed fields. Lensed fields reach fainter objects in smaller volumes, while blank fields sample larger volumes with direct measurements unaffected by lensing models. The two types of field provide complementary statistical samples. Both show the same excess of bright, massive early galaxies over lambda CDM predictions. The broader context of what the deep field images revealed about galaxy morphology, the shapes and internal structures of early galaxies, complements the mass excess in a consistent direction. The standard model predicted that galaxies in the early universe would be irregular and clumpy, lacking the organized disk or spiral structures that characterize large galaxies today. Some of what Webb found at high redshifts was indeed irregular and clumpy, consistent with this prediction. But Webb also detected galaxies at redshift above 6, in the universe's first billion years, showing signs of disk-like morphology and organized internal structure. Forming an organized disk requires a degree of dynamical settling that takes time in the standard model. Finding disk-like structures early implies either that dynamical processes operate faster than expected, or that initial conditions favored more organized configurations than the model assumed. The morphological evidence is less statistically robust than the mass excess, but it points in the same direction. The early universe appears to have been building organized structure faster than predicted in more than one observable way. The confirmation process for high redshift galaxy candidates illustrates how science moves from initial detection to established result, and why the early galaxy problem is now taken seriously rather than treated as a preliminary anomaly. Photometric detection, identifying a candidate at high redshift from its colors across multiple filters, is the first step. But photometric redshifts carry uncertainty. Estimated stellar masses depend on assumptions about the stellar population that may be incorrect. A candidate might not be at high redshift at all, if an unusual spectral energy distribution mimics the appearance of a high-Z galaxy in the photometric bands observed. Spectroscopic confirmation is a required second step, a spectrum identifying specific emission or absorption lines at their expected wavelengths, placing the object unambiguously at a particular distance. For GNZ11, the spectroscopic confirmation from Webb's near-infrared spectrograph was unambiguous. Multiple emission lines appeared at wavelengths consistent with redshift 10.9. The galaxy is where it appeared to be. Its properties, as measured spectroscopically, were not what a galaxy of that age and distance was expected to have. The galaxy's stellar mass function, the distribution of galaxy stellar masses at a given redshift, provides the clearest statistical statement of the problem. Lambda CDM predicts a specific shape for this function at each cosmic epoch, a steep decline at the high mass end, with very few galaxies above a characteristic mass scale that grows slowly with cosmic time. At Z7 to Z10, the model predicts that galaxies above 10 billion solar masses should be extraordinarily rare. What Webb's early deep field data consistently show is that the high mass end of the mass function at those redshifts is higher than predicted. More galaxies at high masses than the model allows. The discrepancy is not uniform across all masses. At lower stellar masses, the model and the observations agree reasonably well. It is specifically at the high mass end that the excess appears. This localization of the problem to a specific regime, the most massive objects at the highest redshifts, is itself informative. The modification needed is one that speeds up the formation of the most massive early structures without affecting the less massive ones, which is a non-trivial constraint on any proposed solution. The chemical evidence from GNZ11's spectrum, specifically the elevated nitrogen-to-oxygen ratio, provides an independent line of evidence for chemical maturity that does not depend on stellar mass estimates. The nitrogen-to-oxygen ratio in the emission lines of GNZ11 was measured by the team led by Roberta Maiolino of the University of Cambridge, published in Nature in 2024. The ratio they found was approximately 3.4 times the solar value. In well-studied nearby galaxies, nitrogen enrichment at this level is associated with stellar populations that have cycled through many generations over several billion years. The CNO cycle in intermediate mass stars builds up nitrogen progressively. Finding this signature at redshift 10.9 in a galaxy 400 million years old is the chemical equivalent of finding bone density markers consistent with a 60-year-old human skeleton in a burial dated to the person's teenage years. The Maiolino team interpreted the nitrogen enrichment as possibly indicating the presence of a dense stellar cluster or globular cluster progenitor in the central region of GNZ11, an extremely compact high-density stellar environment where conditions might allow more efficient chemical processing. This interpretation is scientifically legitimate. The tension remains in the stellar mass, in the luminosity, and in the chemical maturity taken together. No single explanation accounts for all three features simultaneously within the standard framework. The reaction of the theoretical community to the early galaxy excess followed the standard hierarchy that characterizes science's response to anomalous data. The initial response was to look for measurement errors. Multiple groups independently reanalyzed the photometric data using different software pipelines and different assumptions about the stellar population models. The answer was that the excess persisted across methodological variations. Different groups using different methods obtained similar results. The second phase of response explored whether known physical processes not fully included in standard galaxy formation simulations could account for the excess. More sophisticated treatments of feedback, variable star formation efficiencies, and different initial mass function assumptions were examined. None eliminated the discrepancy. The third phase, which is current, involves proposals for genuinely new physics, modifications to the dark matter model, changes to the inflationary scenario, or extensions to general relativity that affect the rate of structure formation. This is where the theoretical community is working now, in papers that appear weekly in the preprint literature. The specific statistical framing of the early galaxy problem, the 5 sigma language, deserves more examination than it typically receives. 5 sigma is often described as a threshold for discovery, but in this context it is a threshold for a different kind of claim, that the model is failing. Under lambda CDM's predictions for the number density of massive early galaxies, the probability of observing what Webb observed in the small volume sampled by the early deep field programs is less than 1 in 3.5 million. This is not an edge of tolerance measurement. This is data that lands far outside the model's expected distribution. Scientists in other fields, medicine, engineering, material science, would consider such a discrepancy decisive evidence that something is wrong with the assumed model. The cosmological community's appropriate methodological caution reflects both the complexity of the observations and the formidable success record of the model being challenged. But the 5 sigma number is not a metaphor. It is a precise statement about how unlikely the observation is under the current theory. The Hubble tension, viewed in historical context, illustrates how long it takes for a well-established model to acknowledge a persistent empirical challenge. The tension was first identified at the 2 sigma level around 2013, when precision measurements from Planck and from the local distance ladder first diverged clearly. At 2 sigma, the response was caution, check the measurements, look for systematic effects, wait for more data. By 2019, the tension had grown to 4 sigma, as both measurement chains improved without converging. At 4 sigma, the response began shifting from, "this is probably a systematic effect," to "this may be a real physical discrepancy." By 2022, some analyses place the tension at 5 sigma with multiple independent calibrations of the local distance ladder. The response then became explicitly theoretical. Something in the model might be missing. This progression from 2 sigma to 5 sigma, spanning roughly a decade of careful measurement, illustrates the measured pace at which well-established models in observational science are allowed to acknowledge fundamental difficulty. The early galaxy problem has emerged faster, but the scientific caution governing its discussion is the same. The question of whether the early galaxy problem and the Hubble tension share a common theoretical root is one of the most actively discussed questions in cosmology right now. Arguments for a common root typically point to the fact that both anomalies involve the early universe. The Hubble tension relates to physics before the CMB was produced, and the early galaxy excess relates to structure formation in the first billion years. If some process in the very early universe, an additional energy component, a modification to the initial conditions, a different treatment of neutrinos, were responsible for one anomaly, a related modification could plausibly affect the other. Arguments against a common root point to the quantitative difficulty of finding a single modification that simultaneously shifts the Hubble constant by the right amount and speeds up structure formation by the right factor without breaking anything else. Papers proposing and analysing potential unified explanations appear regularly in the preprint literature. None has yet achieved broad acceptance as sufficient to resolve both problems simultaneously. The broader issue of what the early galaxy problem implies about the initial conditions of the universe deserves attention. The standard model assumes that the initial density fluctuations produced by inflation followed a specific statistical pattern called a nearly scale-invariant power spectrum, characterized by the spectral index NENS, measured from the CMB to be approximately 0.965. If the early galaxy excess implies that the initial power spectrum contained more power at small scales than this value suggests, that would require either a modification to the inflationary scenario or a systematic error in the CMB analysis at small angular scales. The CMB constraint on NIS comes from fitting a power law across a range of angular scales. If the true spectrum deviates from a power law in a way that adds extra power at small scales while remaining consistent with the CMB measurements at the scales where they are most precisely determined, this could explain faster early structure formation. Testing this explanation requires predicting its signature at scales and epochs that future observations can probe. Specifically, the number counts and mass functions of high redshift galaxies that Webb and future telescopes are measuring. The explanation is testable. It has not been confirmed. The role of numerical simulations in the early galaxy debate deserves careful examination, because simulations are both the source of the model predictions that Webb's data contradict and the primary tool being used to explore potential solutions. Modern galaxy formation simulations, projects like Illustris TNG, Eagle, Simba, and their successors, solve the equations of gravity, hydrodynamics, and a range of implemented physical processes on computational grids spanning volumes large enough to contain statistically meaningful galaxy samples. When calibrated and tested against the galaxy population at redshifts up to ZR4 or ZR5, they worked well. The prediction for higher redshifts was an extrapolation, the result of running the same physics to earlier times where direct observational constraints were unavailable. Webb has now provided those constraints. The simulation's high redshift predictions have been tested against real data for the first time. The test revealed that the simulations underpredict the abundance of massive early galaxies. Whether this reflects missing physics in the simulations or a more fundamental problem with the underlying lambda CDM framework is the question that motivates the current round of simulation development. New projects designed specifically to explore the early galaxy excess are being planned and run now. The specific language used in scientific publications to describe the early galaxy problem signals the field's collective assessment in ways that may not be obvious to non-specialists. When a paper published in Nature describes Webb's findings as presenting a tension with the prevailing theoretical paradigm, the word tension is doing substantial work. In the vocabulary of observational cosmology, tension means the discrepancy between observation and theory is real, statistically significant, and not obviously attributable to known systematic effects. It does not mean the discrepancy is small. It does not mean it will be resolved easily. It means the field has moved past the phase of attributing the discrepancy to measurement error and is grappling with its theoretical implications. When Boylan-Kolchin's 2023 paper describes the early galaxy excess as presenting a 5 sigma challenge to lambda CDM, in the most extreme cases, the 5 sigma number is not rhetorical flourish. It is a precise statistical statement. Scientists in other fields would describe this as decisive evidence that something is wrong with the assumed model. The cosmological community's methodological caution is appropriate given the complexity of the observations. It is also producing public characterizations of the situation that are quieter than the numbers justify. The timeline for resolving the early galaxy problem is realistically measured in years to a decade, not months. Spectroscopic follow-up of the most important candidates is limited by telescope time. Webb's schedule is heavily oversubscribed, with many competing scientific programs. Obtaining the deep, high-quality spectra needed to fully characterize the massive early galaxy candidates at ZR7 to ZR12 requires many hours of integration time per object, and there are many objects to characterize. As spectroscopic data accumulates, the statistical picture will sharpen. The mass estimates will become more precise. The chemical compositions of more objects will be measured. The question of whether the most extreme photometric mass estimates survive spectroscopic scrutiny will be answered object by object. In parallel, theoretical work will narrow the solution space. The process is slow by the standards of a news cycle, but steady and producing genuine scientific knowledge with each observation, whether the result confirms the excess or rules out one candidate explanation. That is how science works in practice, incrementally, carefully, and in the direction of the data. The philosophical implication of the early galaxy problem, the possibility that a well-tested, successful theoretical framework requires significant revision, is worth acknowledging directly rather than leaving implicit. Science's self-image is one of a self-correcting enterprise, in which incorrect models are eventually replaced by better ones as evidence accumulates. This is accurate. But the process of correction is rarely clean or rapid. The geocentric model accumulated epicycles for over a millennium before Copernicus proposed a simpler alternative. The steady-state model of cosmology accumulated anomalies before the CMB discovery in 1965 definitively established the Big Bang framework. Newtonian mechanics accumulated anomalies, the perihelion precession of Mercury, the Michelson-Morley null result, before Einstein's relativity resolved them. In each case, the anomalies were real and documented long before the resolution arrived. The early galaxy problem may be in an analogous position, a well-documented, robust anomaly whose theoretical resolution requires either a genuine extension of the existing framework or a more substantial revision whose form is not yet apparent. Which of these options applies will likely become clear within the next decade as observational programs mature and theoretical work narrows the solution space. What the situation in early universe cosmology right now resembles, more than anything else in recent scientific history, is the period between 1998, when the supernova evidence for accelerating expansion was first published, and the mid-2000s, when the cosmological constant became firmly established as the correct interpretation of that evidence. During those years, the community knew that something important had been discovered but did not yet know exactly what it meant, or how deeply it would affect the theoretical framework. Some researchers argued the supernova signal was a systematic artifact. Others proposed alternative explanations that did not require a cosmological constant. The debate was genuine, conducted in the literature, and resolved by accumulating evidence from independent measurement techniques. The current situation with the early galaxy problem has some of the same character. A clear signal, genuine uncertainty about interpretation, active debate among specialists, and a program of follow-up observations that will either strengthen or qualify the initial results. The difference is that the current anomaly, if confirmed at the level currently suggested, represents a challenge to a part of the lambda-CDM model that was itself only established in 1998. The framework has been tested, refined, and successfully applied for a quarter century. The question Webb is forcing the field to confront is whether that quarter century of success has taken the model to the edge of its domain of validity, or whether the early universe simply contains something that no one yet has the framework to describe. The history of look-back time observation is one of the most productive progressions in 20th century science. Hubble's original deep fields revealed galaxies to Ziwa 2 to Ziwa 3, showing the universe actively forming stars at rates far higher than today. Extended programs pushed to Ziwa 6, then Ziwa 7, exposing the epoch of reionization when the first stars ionized the neutral hydrogen that had filled the universe since recombination. Each new reach in redshift revealed a younger universe. Each younger universe appeared broadly consistent with what lambda-CDM predicted: smaller, less organized, higher star formation rates, lower stellar masses. The trend was clear and the model was tracking it. The extrapolation to Ziza 10, Ziza 12, to the universe's first few 100 million years was confident, not blind, not careless. Confident, because the model had been right about every earlier epoch it had been tested against. When Webb crossed the redshift threshold that Hubble could not, it was crossing into a regime where the model's predictions had not previously been checked by direct observation. What it found there was not more of what the model predicted at lower redshifts, scaled smaller. It was something structurally different. The specific question astronomers were asking before the first Webb deep field data arrived was quantitative and precise. How many galaxies with stellar masses above a given threshold should exist per unit volume at each redshift? This galaxy stellar mass function is one of the most fundamental predictions of galaxy formation theory. It encodes the combined effects of dark matter, halo growth rates, gas cooling timescales, and star formation efficiencies across cosmic time. At Z02, Z03, Z04, redshifts, Hubble could access reliably. The measured mass function agreed with simulated predictions to a level that validated the entire framework. The agreement was not perfect at every mass and every redshift, but it was close enough that theorists were confident about the qualitative form of the mass function at higher redshifts. Webb's first deep field data produced mass function measurements at Z7 to Z10 that disagreed with those predictions systematically, consistently, and in the direction of more massive objects than expected. The Hubble Ultra Deep Field image, the 2004 image that revealed 10,000 galaxies in 1/10, the apparent area of the full moon, shaped an entire generation of astronomers' intuitions about what the early universe should look like. The galaxies at the image's highest redshifts, Z5, Z6, appeared small, irregular, clumpy, exactly what the model predicted. The inference was that at higher redshifts galaxies would be even smaller, even more irregular, the early universe containing only the roughest seeds of the structures that would grow into today's galaxy population. This was not a speculation. It was a quantitative prediction derived from a model that had been tested against decades of lower redshift observation. Webb's ability to look cleanly at Z8, Z9, Z10, Z11, the redshifts where the model's small and irregular prediction should have been most emphatically confirmed, instead showed objects that were neither as small nor as irregular as the model required. The prediction was not wrong in every detail. Some high redshift galaxies are small and irregular. What is wrong is the high mass end of the distribution. Too many large objects, too early, assembled faster than hierarchical growth under lambda CDM can physically achieve. The deep field images also revealed something less often discussed in popular accounts of the Webb results. The sheer number of galaxies visible in a small region of sky is itself an observational constraint on cosmological models. The number density of galaxies at different redshifts, how many galaxies per unit volume exist at each cosmic epoch, is a direct lambda CDM prediction that can be tested by counting galaxies in deep field images. These number counts agree with the model reasonably well at intermediate redshifts. At the highest redshifts Webb can probe, early results suggest that while the count of galaxies is not dramatically different from predictions, the brightness and mass of those galaxies are. The universe appears to contain approximately the right number of early galaxies. The problem is that those galaxies are too bright and too massive for the model to accommodate. A discrepancy in number counts alone could be explained by missing objects below the detection threshold. A discrepancy in the mass and brightness of detected objects at an otherwise consistent number, density points towards something wrong in the model's description of how mass assembles within individual halos, rather than in the number of halos that exist. The Laber et al.'s 2023 paper, the one that presented 6 massive galaxy candidates and triggered the most sustained theoretical response, was carefully, even cautiously worded. The authors noted that photometric redshifts carry inherent uncertainties. They acknowledged that some candidates might have contaminated photometry from foreground objects. They explicitly stated that spectroscopic follow-up was needed before firm conclusions could be drawn. This caution is appropriate scientific practice, not evasion. But the caution was sometimes interpreted outside the scientific community as suggesting the results were preliminary or likely to disappear under scrutiny. They have not disappeared. Spectroscopic follow-up has confirmed multiple candidates at high redshifts, though at stellar masses somewhat lower than the initial photometric estimates in some cases, a pattern consistent with the uncertainties the authors identified. Lower confirmed masses help quantitatively. The population-level pattern does not disappear. The systematic excess of bright massive early galaxies over lambda CDM predictions persists across multiple independent datasets, analysed by independent teams. The caution of the original paper was scientific appropriateness. The persistence of the pattern after scrutiny is scientific confirmation. The false hope ladder in the early galaxy problem has a specific structure that matters for understanding why the problem is considered serious rather than merely puzzling. Each proposed rescue attempts to explain the apparent mass excess by attributing it to something other than genuinely massive galaxies. Photometric uncertainty might overestimate masses. AGN emission might inflate apparent luminosity. Population 3 stars might produce more light per unit mass than nearby stellar populations. Each of these explanations is physically legitimate and worth pursuing. Each one also has a specific observational test, spectroscopy, that constrains the stellar population assumptions, detailed spectral modelling that separates AGN emission from stellar emission, detection or non-detection of spectral features characteristic of population 3 stars. What makes the early galaxy problem structurally different from a simple measurement uncertainty problem is that these tests have been applied to the best characterized examples, GNZ11 above all, and the rescues have failed for those examples. GNZ11's nitrogen enrichment argues against population 3 dominance. Its spectroscopic mass, while lower than the photometric estimate, still places it well above the lambda CDM predicted maximum for its epoch. The best studied object in the sample is also the one most resistant to rescue. The cascade of evidence from GNZ11 specifically, stellar mass, luminosity, chemical composition, spectroscopic redshift confirmation, detailed spectral modelling, makes it the cleanest individual example of the broader pattern. But it's important not to treat GNZ11 as the entire case. The case rests on population-level statistics, the consistent excess of bright, massive galaxies at high redshift, across multiple independent deep field programs. GNZ11 is the central specimen, not because the case depends on it alone, but because it is the object that has been studied most thoroughly, and therefore provides the most detailed individual test of every proposed rescue. It is the object where the false hope ladder has been climbed most completely, and found to be insufficient. What is true of GNZ11 in detail is likely to be true of the broader population in aggregate. The model failed its best characterized test case. The population-level statistics suggest it is failing more broadly. The specific prediction lambda CDM makes for the galaxy stellar mass function at high redshift, the prediction that Webb's observations are violating, is derived from a chain of physical reasoning that makes it resistant to simple modification. First, the initial density fluctuation spectrum is constrained by the CMB to a nearly scale-invariant power law with spectral index n as s approximately 0.965. This constrains the number and mass of dark matter halos that can form at each epoch. Second, the conversion of dark matter halo mass into stellar mass involves gas cooling, fragmentation, and star formation, regulated by feedback processes. Third, the observed feedback in the local universe, characterized in detail by the same simulations that fail at high redshift, sets the star formation efficiency in the models. The prediction at high redshift is the output of all three of these inputs. Changing the prediction at high redshift without changing one of these inputs is not possible. Changing any of them while preserving all of the successful predictions at lower redshifts is extremely constrained. This is why the early galaxy problem is considered a structural challenge rather than an adjustable parameter problem. The timing of the early galaxy problem relative to Webb's operational history is relevant for understanding its current status. Webb launched in December 2021 and began science operations in mid-2022. The first deep field images were released in July 2022. The first papers identifying the high redshift galaxy excess appeared in late 2022 and early 2023. Boyle and Kolchin's statistical analysis appeared in 2023. Maslino's nitrogen-oxygen ratio paper appeared in 2024. The field has been grappling with this problem for approximately 2 to 3 years. In the context of a problem that requires years of spectroscopic follow-up, theoretical development, and new facility construction to resolve, 2 to 3 years is very early. The fact that the problem has persisted and sharpened under scrutiny in that time, rather than diminishing as initial measurements were refined, is the primary indicator that it is real and significant. The fact that it has not been resolved in 2 to 3 years is not unusual for a fundamental problem in observational cosmology. The Hubble tension is a decade old. The current situation is one of a confirmed problem with no confirmed solution, at the beginning of the observational and theoretical campaigns designed to produce one. The near-term observational program targeting the early galaxy problem involves specific instruments with specific timelines. Webb will continue accumulating deep field data, with spectroscopic follow-up programs targeting the most scientifically important candidates. The ALMA Observatory provides independent millimeter-wave measurements of dust and gas in high redshift galaxies, traces of star formation activity and molecular gas content that do not depend on the optical and infrared photometry at the center of the current excess. If ALMA measurements of the same high redshift galaxies confirm the mass excess that Webb's photometry suggests, that independent confirmation would significantly strengthen the case. The Chandra X-ray Observatory can search for X-ray signatures of direct collapse black holes and active galactic nuclei in high redshift systems. The extremely large telescope, scheduled to see first light later this decade with its 39-meter mirror, will take spectra of high redshift galaxies with resolution and efficiency that Webb cannot match. The Roman Space Telescope will survey areas orders of magnitude larger than Webb's deep fields at comparable sensitivity, providing statistical samples large enough to precisely characterize the galaxy mass function at high redshift. Each of these instruments tests a specific prediction of the candidate explanations. Each will either find the expected signatures or exclude them. The history of cosmological model revisions provides context for understanding what a resolution might look like and how long it might take. Lambda CDM itself was not the original framework. The cosmological constant was added to the standard model in 1998. After supernova surveys found the universe's expansion was accelerating rather than decelerating. That addition changed the universe's energy budget from roughly 30% matter and 0% dark energy to the current 5% ordinary matter, 27% dark matter, 68% dark energy. The revision was not immediately accepted. It took several years and multiple independent confirmations from CMB measurements, large-scale structure surveys, and additional supernova programs before the cosmological constant became the established consensus. The current situation, where Webb's observation suggests that something in the framework's treatment of early structure formation is incomplete or incorrect, is qualitatively similar. A clear observational anomaly, a range of candidate explanations being tested, a timeline measured in years to a decade, and no consensus solution yet available. The historical analogy does not predict whether the resolution will require a modification to an existing framework or a replacement of one of its foundational assumptions. It predicts only that the resolution, when it comes, will have been preceded by a period of exactly the kind of productive, scientific uncertainty that the field is currently in. What distinguishes the current period in early universe cosmology from earlier periods of anomaly is the precision and clarity with which the problem is defined. Previous anomalies at high redshift, the galaxy number density problem at intermediate redshifts, the Hubble tension's early manifestations, were ambiguous enough to sustain debate about whether they were real or systematic. Webb's data are not ambiguous in the same way. The telescope was specifically designed to observe the epoch where the current excess appears. Its observations have been independently confirmed by multiple teams using multiple analysis methods. The spectroscopic confirmations have eliminated the redshift uncertainty that allowed earlier photometric detections to be dismissed. The chemical evidence from GNZ11 provides a line of argument entirely independent of stellar mass estimation. The problem is sharply defined. The solution is not. That combination, a well-defined problem without a confirmed solution, is exactly the condition under which theoretical progress is most productive and most urgent. The engineering choices in Webb were not merely practical, they were philosophical. A telescope operating at -233 degrees Celsius, positioned behind a tennis court-sized sun shield at 1.5 million kilometers from Earth, with no possibility of servicing or repair, represents a different kind of relationship with the instrument than Hubble. Hubble could be, and was, serviced by astronauts 5 times. Its instruments were upgraded. Its mirrors were corrected after the spherical aberration discovered at launch. Webb cannot be reached. Every decision about its design, every material choice, every optical specification had to be correct the first time. The engineering teams that built it knew this. The result of that constraint is a telescope that was overspecified where specification was possible and monitored exhaustively at every stage of testing. Webb's optical performance at L2 exceeded specifications in part because the testing regime that preceded it was designed to catch failure before launch, under conditions as close to the operating environment as Earth-based facilities could simulate. The instrument works. The data it returns are reliable. What the data say about the early universe is therefore not a function of instrumental uncertainty. It is a function of what the early universe actually contains. The 48.25 grams of gold on each mirror segment, less than a wedding ring, is one of the more counterintuitive material choices in Webb's design. Gold is chosen not for its cost or its symbolism, but for a specific and measurable optical property, its reflectivity in the infrared part of the electromagnetic spectrum. At the wavelengths Webb needs to detect, from 0.6 to 28 microns, gold outperforms aluminum, silver, and every other practical coating material in terms of the fraction of incident light it reflects rather than absorbs. Gold reflects approximately 99% of incident infrared radiation across the wavelengths Webb detects. An absorbed photon becomes heat. On a telescope operating at -233 degrees Celsius, stray heat from mirror absorption is a source of thermal noise that degrades sensitivity. The gold coating is not luxury. It is precision engineering in service of the lowest possible noise floor. The ancient light arriving from GNZ11 after 13.4 billion years of travel is extraordinarily faint. Every design choice in Webb that reduces the noise floor expands the universe it can see. The confirmation of GNZ11's properties via spectroscopy, rather than photometry, matters for understanding why the early galaxy problem is now considered established rather than preliminary. photometric measurements infer properties from a galaxy's brightness in different wavelength bands, using model assumptions about the stellar populations and dust that produce that brightness. The assumptions introduce uncertainties. Spectroscopy identifies specific emission and absorption lines produced by specific atomic transitions in specific elements at specific temperatures and ionization states. These lines appear at precisely predictable wavelengths for any given redshift, and their ratios encode information about elemental abundances, star formation rates, and physical conditions in the galaxy's gas. Webb's near-infrared spectrograph confirmed GNZ11's redshift from multiple independent spectral lines, not one, but several, appearing at the expected wavelengths for Z Untitanate 9. The confirmation is overdetermined. Removing any one spectral line leaves the others to confirm the same redshift. And the chemical information encoded in the line ratios, the nitrogen to oxygen ratio of 3.4 times solar, is a measurement that photometry cannot produce at all. The spectroscopic confirmation of GNZ11 is not a refinement of the photometric detection. It is an independent measurement of a different kind, with different systematic uncertainties, that agrees with the photometric result and extends it with information the photometry could not provide. The practical technique of photometric redshift estimation deserves brief attention because it is the method that produced the initial catalogue of high redshift candidates, and because understanding its strengths and limitations is necessary for evaluating the weight of the evidence. The Lehman break, the sharp drop in a galaxy's light output at wavelengths below 91.2 nanometers, caused by neutral hydrogen-absorbing ultraviolet photons, shifts to longer wavelengths as redshift increases. At Z7, the break falls in the near-infrared at roughly 700 nanometers. At ZES 10.9, it falls at approximately 1 micron. By observing a galaxy through multiple filters and identifying in which filter the galaxy's light drops sharply, astronomers can estimate the galaxy's redshift without a spectrum. The technique is efficient. Many galaxies can be characterized simultaneously from imaging data, but carries uncertainty of typically 10 to 20% in redshift, larger for faint objects. More critically, unusual spectral energy distributions can mimic the appearance of high redshift galaxies in photometric data, producing false positives. Spectroscopic follow-up eliminates these false positives by requiring the identification of specific spectral lines. For the Webb early galaxy candidates, photometric redshifts identified the targets. Spectroscopic follow-up has confirmed many of them. The confirmed candidates are the scientifically robust ones. They are the ones showing the mass excess that persists after all methodological scrutiny. The statistical significance of the early galaxy excess, expressed as 5 sigma in the most extreme cases, needs to be understood in the context of what specifically is being compared. Boylan-Colchin's analysis asked, given lambda CDM's prediction for the number density of very massive dark matter halos at high redshift, and given the observed efficiency with which halos of that mass convert gas into stars, what is the probability of observing the Lab et al. Galaxy candidates in the volume sampled by Webb's early deep fields? The answer, less than 1 in 3.5 million, is a statement about the joint probability of observing multiple extreme objects in a small survey volume, if the model is correct. It is more constraining than asking about any single object in isolation. The reason is that the probability of observing multiple independent extreme objects multiplies. If each object is individually unlikely under the model, observing several of them together is even more unlikely. This joint probability is what the 5 sigma threshold reflects. It is not a statement about the most massive single galaxy. It is a statement about the population of massive early galaxies as a whole, and whether that population is consistent with Lambda CDM's predictions for how many such objects should exist. The question of what would constitute definitive resolution of the early galaxy problem, what specific observational results would either confirm the Lambda CDM challenge or explain it away, has been specified in the scientific literature. For the challenge to be definitively confirmed, spectroscopic confirmation of multiple massive early galaxy candidates with stellar masses well above Lambda CDM's predicted maximum at 5 sigma statistical significance from independent survey programs would constitute robust evidence of a real model failure. For the challenge to be explained within Lambda CDM, spectroscopic mass estimates for the current candidates would need to come in substantially lower than the photometric estimates, low enough that the population level excess falls within the model's predictions, and a physical mechanism would need to be identified that explains both why the photometric estimates were inflated and why that inflation would be so systematic and widespread. The spectroscopic data accumulated so far has confirmed some reduction in estimated masses relative to photometric values, but has not brought the population-level excess within the model's predicted range. Both outcomes remain possible as more spectroscopic data accumulates. The scientific community is watching the data closely. Lambda CDM success at lower redshifts, the success that makes the high redshift failure surprising rather than expected, is worth enumerating specifically because it defines the constraint that any revision must satisfy. The CMB power spectrum, the pattern of temperature fluctuations across the sky, measured with extraordinary precision by Planck, is predicted by Lambda CDM from the same initial conditions that seeded all subsequent structure formation. The agreement between prediction and observation is extraordinary. Big Bang nucleosynthesis. The model predicts the primordial abundances of hydrogen, deuterium, helium and lithium produced in the first 3 minutes after the Big Bang. The predicted and observed abundances agree across 8 orders of magnitude in nucleon density. Baryon acoustic oscillations. The characteristic scale imprinted in the large-scale distribution of galaxies by sound waves in the early universe's plasma, a predicted scale visible in both the CMB and in galaxy surveys. The scale is found at the predicted distance. Large-scale structure, the statistical properties of the cosmic web of filaments, clusters, and voids on scales of hundreds of millions of light-years, predicted by the same Lambda CDM initial conditions and confirmed in galaxy redshift surveys spanning most of the observable universe. Each of these successes constrains what modifications to the model are permissible. Any replacement framework must recover all of them, while also explaining what Lambda CDM gets wrong at high redshift. The communication gap between what the early galaxy data shows and what appears in public-facing communications from major space agencies and observatories reflects a genuine structural difficulty in science communication rather than any intent to mislead. Scientists who spend years developing a theoretical framework and decades of their careers working within it do not comfortably describe that framework as failing. The appropriate scientific response to anomalous data is skepticism, scrutiny, and a search for explanations within the existing framework before concluding that the framework requires revision. This is methodologically correct and essential. At the same time, this appropriate methodological caution produces public communications that understate the severity of the situation when measured against the statistical language the scientists themselves use in the published papers. The 5 sigma figure, less than 1 in 3 million probability under the null model, appears in the scientific literature. The public-facing communications describe the results as surprising and challenging our understanding. Both descriptions are accurate. They are not equally informative. The broader context of cosmological anomalies extends beyond the early galaxy excess and the Hubble tension. The sigma-8 parameter, which characterizes the amplitude of matter density fluctuations on scales of 8 megaparsecs, shows a tension between the value inferred from the CMB and the value measured by weak gravitational lensing surveys of the nearby universe. Large-scale structure surveys show some evidence for anomalies in the distribution of matter on the larger scales. The CMB itself shows large-scale features, alignments and asymmetries on the scale of the full sky that appear unlikely under a perfectly isotropic lambda CDM universe. Each of these is individually explicable by systematic measurement effects or statistical fluctuations. Taken together, they form a pattern of a theoretical framework that is producing predictions in consistent tension with increasingly precise observations across multiple independent sectors. The early galaxy problem is the most statistically significant and most clearly connected to a fundamental physical prediction, but it is part of a broader picture of a theory being tested at the boundaries of its validity. What is unusual about the current period is not that anomalies exist. Anomalies are part of normal scientific progress. What is unusual is the number of independent sectors where the anomalies are appearing simultaneously, as measurement precision has improved to the level where genuine theoretical failures become distinguishable from statistical fluctuations. The telescope is named after James E. Webb, who administered NASA from 1961 to 1968 and oversaw the Apollo program's development. The naming recognizes administrative and organizational achievements rather than scientific ones. Webb was not an astronomer. This is occasionally noted as ironic, given that the telescope carrying his name is producing results that may require revising the theoretical framework that dominated his era of space astronomy. But the naming reflects a genuine insight. The observatory-level achievements that made the scientific results possible required the kind of sustained institutional and political commitment that Webb exemplified. The science proceeds from the engineering, and the engineering proceeds from the organization, and the organization proceeds from the commitment. All three were required. The anomalous data arriving from L2 is the consequence of 3 decades of sustained effort across all 3 domains. Whether the data leads to a refinement or a replacement of current theory, it is producing the most precise test of cosmological structure formation predictions that has ever been conducted. That test is ongoing. The telescope is still running. The concept of hierarchical assembly, the central process by which lambda CDM predicts galaxy formation, is worth making viscerally concrete, because the early galaxy problem is fundamentally a failure of this process to match observations at high redshift. Hierarchical assembly means structure grows from small to large. The first objects to form are the smallest dark matter halos, structures containing perhaps 1 million solar masses of dark matter. These merge over time into progressively larger halos. Galaxy-scale halos form over hundreds of millions of years. Cluster-scale halos require billions of years. The process has a maximum rate that is set by the density field of the early universe, by how many overdense regions are available to merge, and by how fast gravity can draw them together. At redshift 10, 480 million years after the Big Bang, this process has had less than 4% of the age of the current universe to operate. GNZ11's stellar mass of 1 billion solar masses implies a dark matter halo of roughly 50 to 100 billion solar masses. The formation of a halo that massive in 480 million years, through hierarchical merging from a nearly uniform starting point, is what the model says cannot have happened. Not unlikely, cannot. The model's prediction of the maximum halo mass at that epoch is a derived consequence of the initial density field, not an adjustable parameter. The distinction between the number of galaxies and the mass of galaxies at high redshift is crucial for understanding why the early galaxy problem is considered structurally significant, rather than merely a calibration issue. If Webb had found too many galaxies at high redshift, more objects than predicted, even at low masses, the resolution might be relatively straightforward. Perhaps star formation was more widespread than expected, forming many small objects from many small halos. This would be a quantitative disagreement about star formation rates, the kind of discrepancy that could be accommodated by adjusting efficiency parameters within the model. What Webb found instead is not too many galaxies at low mass, but too many galaxies at high mass. Mass is more directly constrained by dark matter halo formation than star formation efficiency is. A galaxy with 1 billion solar masses of stars requires a dark matter halo of 50 to 100 billion solar masses. That halo requires a density fluctuation in the early universe large enough to collapse that much mass on that timescale. The density fluctuation spectrum is constrained by the CMB. The timescale is constrained by the Big Bang. Neither is an adjustable parameter. The mass excess points directly at a fundamental prediction of the theory, not at a process that might be tuned within the theory's framework. The word model in the phrase lambda CDM model sometimes causes confusion about the nature of the claim being made. A model in physics is not a guess or an approximation in the colloquial sense. It is a precise mathematical description of a physical system, built from well-established principles and constrained by extensive observational data. Lambda CDM is constrained by approximately a century of cosmological observation, including the CMB power spectrum, the large-scale distribution of galaxies, the abundance of light elements, the accelerating expansion rate, and much more. The model's predictions are not qualitative trends. They are specific numerical values for observable quantities. When Webb's observations disagree with those values at 5 sigma, the disagreement is a quantitative statement about how far outside the model's allowed distribution the data falls. This is what makes the early galaxy problem scientifically significant rather than a matter of interpretation or perspective. The model says one thing, the observations say another. The gap between them is not ambiguous. The implications of the early galaxy problem, if the excess is confirmed at the level currently suggested, extend beyond cosmology to fundamental physics. Lambda CDM is built on general relativity, the quantum field theory description of particle physics, and the inflation paradigm for the generation of initial conditions. If the early galaxy excess requires new physics, the most likely candidates are modifications to inflation, which sets the initial density fluctuation spectrum, or to the treatment of dark matter, which governs how halos form and merge, or to the relationship between baryonic matter and dark matter halos in the earlier structures. Each of these touches foundational aspects of the theoretical framework that underlies not just cosmology, but particle physics and gravitational physics. A resolution that requires modifying the inflationary scenario, for example, would have implications for our understanding of the universe's first moments and the origin of structure at the most fundamental level. The stakes of the problem are therefore not merely astronomical, they are physical in the deeper sense. The grain of sand patch of sky at the centre of this story, the region so small that its angular size on the celestial sphere is measured in arc-seconds rather than degrees, is not unique. Any patch of sky of that size pointed in any direction away from the plane of the Milky Way would contain a similar depth of galaxies. Webb has observed multiple such fields. The Sears program, the JADES program, the Cosmos Webb program, each covering a different region of sky, each using slightly different observational strategies, each analysed by independent scientific teams. The early galaxy excess appears in all of them. The phenomenon is not localised to one patch of sky. It is not a coincidence of cosmic variance, the statistical accident of having observed an unusually overdense region. It is a consistent feature of the early universe at the redshifts Webb can probe. The grain of sand held at arm's length is a representative sample, What it revealed is what the early universe looks like, and what the early universe looks like does not match what the standard model predicted it would look like. The signal persists. The gap is real. The telescope is still running. Go back to the grain of sand. Hold it at arm's length. Cover that pinhole of sky. The one that contained nothing detectable, nothing catalogued, nothing any previous instrument had flagged as worth the observation time. James Webb stared at it, and inside that invisible window, among the thousands of galaxies that emerged from 12 hours of accumulated exposure, sat GNZ 11, light that left its source 13.4 billion years ago. A billion solar masses of stars assembled in a universe 400 million years old, carrying chemical fingerprints of stellar generations that should not yet have had time to complete. Sitting in the data. Confirmed. Real. The honest verdict from the first years of Webb science is this. The early universe is not arranged the way the standard model predicted it would be. The galaxies at high redshift are too bright, too massive, too chemically mature for their age. The gap between the prediction and the observation is not narrowing as the data improves. It is becoming more precisely defined, and the description is ours. The universe does not adjust to accommodate the theory. Something assembled GNZ 11 in the dark, before the Milky Way existed in its current form, before the Sun had any reason to form, before any planet in the observable universe had cooled enough for liquid chemistry to occur. Something built 1 billion suns worth of material into a single bound, enriched, multi-generationally processed galaxy before the universe had completed its first 400 million years. The model did not predict it. Webb found it. The telescope is still running. If this is where you come to sit with what is actually known about the universe, a subscribe and a share tonight would help more people find it. The grain of sand is still there.